Okay. Let's get my screen shared. I think we're probably gonna do a lecture tomorrow rather than the lab because we're not quite where we want to be for the lab, and I don't see the point in rushing it. So some of the stickiest material we got to get through. So maybe the lab will be Monday. So we've had to do that before and survived, so I guess it'll probably be okay. Um, Right. So we started in yesterday on the neural network deck here. You'll remember this image, I hope, right? And you realize, if you didn't already realize at all, an artificial neuron is it's a mathematical function, a parameterized function. It's got these W's, it's got this B, okay? And if you know the W's and the B, it's just a matter of putting them together, forming this sum, and then passing it through some F. Okay, that's the little bit, that piece is a little mysterious on the slide. What is F? No big deal, as I'll show you in a minute. We usually use pretty simple Fs these days. Hopefully you get some sense of why the naming is what it is, like weights, right? You know, which input is important, which one deserves a weight, right? The one that deserves weight and has a larger number here, whether it be positive or negative, is going to have a bigger impact on that sum, and thus on what comes out of the function f. And the bias is just, if the bias is high, then it's a neuron that wants to give positive outputs. It's biased in a positive direction, or if it's negative, it will want to give negative outputs if our f looks like that. Okay, so hopefully that makes at least rough sense. Okay, now what is f? Here are like the traditional ones that actually look like that picture. These are actually not the ones that are most used today. We use even simpler ones, but something like this, logistic transfer function, this has been around forever. It's not very complicated. It does have an exponential in it. Hopefully, you can go through and think about this, right? Well, what happens when x is really big? When x is really big, this becomes really negative. This becomes really small. So f becomes 1. What about if x is really big but negative? Okay, then this is positive. This becomes positive, and this becomes 0. So it's like the picture, but with 0 down here, right? And you can do the same analysis for the second most popular of these is maybe this one up at the top. And this one's also going to go between 0 and 1. Occasionally people make it go between -1 and 1. I mean, obviously you can just add, multiply by 2 and subtract 1. And you can convert any of these to something that goes between with a range between -1 and +1. Okay. Um, these things are still important today. I just was reading a paper. I'm late because helping review a paper has a model in it. That model is a logistic model. It uses this representation. It's super popular over in OR land, super popular in econometrics and biometrics and a bunch of different areas. Often their models will just be one neuron with a logistic output. That's it. Okay, but that's different enough in capability from a normal linear regression model that it seems to add a lot of value for folks because it's used a lot. Okay, all right. This is actually the one that's used the most these days, and which we'll probably use mostly in this class. It's called a ReLU activation function. That's what that F is called, the activation function. ReLU stands for rectified linear units. So it's basically linear, except that if the input is negative, it just gives a 0. Okay? So it's very easy to write this function mathematically as the max of 0 and x. And it's just the next thing, just, ever so slightly more difficult than dealing with just a normal linear unit. To the point where you might think, let's just make them all linear. And then you realize that actually a huge network full of linear units is equivalent to one linear unit, because that's the math of linearity. It never gains power by adding more units. Okay, but just this little bend here that makes it not quite linear, Now, this is what's being used in all your trillion parameter models out there. Okay. All right. It is still the case that linear units are used sometimes. Again, not just one neuron with a linear output, not a network full of linear units, because as I said, that makes absolutely no sense. That's just a computationally intensive way of doing linear regression. But one linear unit maybe at the output of a bigger neural net, sure, why not? Do it all the time. We'll do it in the next lab, Andy.
Roger, add something, sir. This may be well beyond the scope of what we're doing, so how do you decide which one of these to use?
So there's no good way. I mean, I'll say a couple words that limit the scope, but many have been tried, and the popularity of them has risen and fallen. It's at this point, I don't think people think that ReLU has any magic to it. People have settled on ReLU just because it's so darn simple. It's simple to implement computation, burns very few cycles when it actually runs. It doesn't seem much worse than the other alternatives. So why not, right? I think that's more the attitude.
I'm sorry to ask this, but
Yeah. Don't be sorry.
I don't understand why we would, so they take everything else in this process when you're describing the neuron of the neural network makes sense, but you're gonna take your inputs, you're gonna assign the weights, you're gonna sum all those, you're gonna add a bias, and then you're like, we're just gonna feed it into this random function over here. Why? Who decided to do that? What did it do?
Well, so again, so you have to understand that people did start off with just like a linear function. That's like if a linear function, one example of a linear function is the identity function, in which case it might as well not be there. So we remove that arbitrariness. It's just gone. F is gone. The problem is you can't do much with it. Then you're just doing linear regression. You can do exactly what you can do with a linear regression model. So in domains where there's plenty of uses for linear regression, nothing against linear regression. I would never use a neural net if I thought I could get away with just linear regression because it's just so much more cut and dried how to do it. But
what
people
are you trying to do? You say you can't do much, like when you feed your data through a ReLU.
Well, that's what you're okay. So right. So like all the applications of neural nets that you hear about, right? So starting with modeling functions, right? And going on to classifying objects and going on to evaluating what actions are good, going on to representing probability distributions. None of those make sense with a linear unit. You got to have something else. And follow up if you can.
For example,
I'm not satisfied with my answer either.
in the same.
Yeah.
For example,
Yeah.
if you wanted a super simple neural net that could just tell you if a picture was a dog or a cat.
Yeah.
You
Only
want
one bit
to
output. Yeah.
take your inputs and assign your weights and add your bias, and then you would want to shove it through a activation function that will tell you if it's close to 1 or close to 0.
So are we talking about a one neuron? One neuron, or are we talking about
of
neural
different
net?
neurons.
What's
But
that?
a bunch of different
A
neurons.
bunch of
The
neurons.
output is going to be a 0 or 1. It's going to be a cat or dog.
Right. Well, that is often so the way we do that, that's a classification problem. And the nice way to get an output for a classification problem is to get it as a conditional probability. We want the probability it's a cat versus a dog. Of course, if you got those are the only possibilities. If I give you the probability that it's a cat, my probability that's a dog is 1 minus that. So that's something that probability. Now you see, well, that's constrained to a range, right? Like if you do a linear model and you fit the probability data, which you can totally do, you can jam it into Excel right now and do linear regression, but you'll get probabilities greater than 1. You get negative probabilities, depending on your data. The model just isn't going to be constrained in a way that's really natural for you. You might still be able to do a job of that, But back to what I was saying, but what you won't be able to do is if you're not satisfied and you're like, yeah, it does well in these easy pictures, but now I get these more complicated dog and cat and shadows and stuff and they're failing. And now what do I do? You can't throw more linear units on there to make it work better. That just won't work. Whereas if you're using one of these approaches, it stands a chance of working.
And I'm not even sure if I'm asking the correct question here, but just as obviously no real numbers here, but if we imagine you had made the dog cat identification algorithm and you had two different machines, one was just all linear.
Yeah.
And the other one was with these, how would those, I know you're saying, hey, on this, you can apply additional units to more neurons will actually increase the accuracy. If you could just talk a little bit about how those two machines would be different. If a guy said, I don't need relus, I'm just gonna.
Right, so it's a little abstract, but if you'll accept that, any data that you put in, even an image or any kind of data you put in is just a vector of numbers at the end of the day. Even if it isn't naturally a vector of numbers, it's people's addresses or something weird like that. You're going to have to convert it into numbers to get any traction in this kind of a model. So that means that in some kind of a space, a really high dimensional space, not a two-dimensional one like this blackboard, there's going to be, the cats will be in one location and the dogs will be somewhere else, right? And if it looks like this, cats versus dogs, such that there is a line in between the two, then a linear model will be able, might not do it, might not say between 0 and 1, it might not be so nice, but you could use a linear model or one neuron to go and discriminate these. Okay? The weights will point in this direction as a vector, right? And then just thresholding that output will say what side you're on. Okay. But the problem is, what if there's, dogs are not cats, but what if the situation is just a lot more complicated and it looks like this? Okay, there's definite regions of, cats over here, and there's this real ugly region in the center for dogs. Now what? Okay, so just trying to put a line down and say, well, which side does the dogs on, which side of the cats on? What, if you do a linear regression on this, it will do its best possible job. It'll draw some line, and it will try to maximize its performance, but the performance will be terrible, and there won't be an easy way to improve.
That answers my question. Thank you.
Good. Better?
That was better.
All right.
That made more sense.
All right. Let's keep going. All right. So yeah, again, linear units, not that they're useless. You'll see it even in the next lab. Okay. I want to just say, I think there's maybe a little, we'll maybe come back around to this, at least a little bit later on. There are other types of neuron that are actually still really important today, like the ones so-called convolutional neural net units. Those are real popular for image processing, since we're just talking about images of cats versus dogs, right? In many ways, they work like the prototypical neuron I just gave you, but they do weight sharing. Okay, I mean, it should be no problem with that, right? If I said, instead of the one picture of a neuron, clone it. Oh, and they're going to share weights W2, W3, and W4. The other ones they'll learn separately, but they have to share those. That's nothing mind-blowing, right? And it's strictly just to make things tractable. So you can learn them faster, and so the models don't get ridiculously large. Okay. There are also in large language models, they also have something you can squint at and say it's similar to a neuron. I actually had to look up today. Do people normally call them neural networks? And the answers I was getting was yes. People definitely call LLMs that sometimes these are called transformer networks. So we'll talk about those more toward the end of the course, a little later. They definitely call them neural networks, but they don't use, neurons that are quite standard. I wouldn't say they're worlds away in complexity, but they're different. And we'll talk about how later. So just a nod to say this isn't the whole world, but it's most of them. And if you know the standard neurons and you know these and you know these, boy, now you know 90-something% of what people are using out there. It's be the rare product or research paper that uses something else. Okay, so we talked about individual neurons. A neural network, of course, is just a bunch of individual neurons connected together. Okay, and this is kind of a prototypical picture of a neural net. Now, some of these are normal neurons and some are not. They're always kind of drawn this way. So the ones that are not normal neurons are these ones in the input. So what these are really there to do is just to represent the fact just to make the picture kind of more homogeneous, okay? And they're really just there to take an input and send it to all possible locations. I really don't even have to draw those as neurons, but that's what we always used to do. I don't know what people do these days. I guess you could imagine me just taking these out and just putting a line that then forks and just goes to every possible neuron there, so they all get the information. Okay? They all want to see input 1, they all want to see input 2, and on down. But the other ones are neurons that match our description. You'll notice that, and again, there's nothing written in stone that you have to do it this way, but in fact, people organize these neurons into layers. I mean, the inputs are special, so that could always be considered a layer. But typically, people then just draw some number of layers of some size with some numbers of neurons in them. And they do that in a very flexible and pragmatic way. And usually there is not a lot of guidance from theory to say, well, how many layers should I use? How big should each layer be? Those are really empirical questions. So like, okay, would you be better off with twice the number of layers you have? I don't know. Try. That's kind of the answer. You're working on a new domain where you really have no idea. Well, get a research paper and see what they did. Try to do something similar to them. It's nothing real satisfying for an answer. Yeah, we've never gotten smarter about that over my lifetime, and I don't expect to get much smarter about that for kind of for practical reasons. Okay, this layer out here is called the output layer, again, for obvious reasons. So that's producing the outputs you're actually going to use for something. There isn't always one. There could be 2 and 3 or a million or whatever. Doesn't matter. I just happened to draw it with 1 here. And then all the layers that are in between, there's just 1 here, are called hidden layers. And all that means is it's because we don't directly see their outputs. They're clearly doing something that's part of the computation and presumably vital to getting the right answer, but we don't actually look at those outputs directly unless have our research hats on and we're trying to figure out some obscure question. So outputs, as you see, are seen, but they're seen by another neuron, not by us. Okay. Whereas this would be our 0 to 1, it's a cat versus it's a dog probability. Okay. Questions about this? Okay, that's the general picture. All right. Now, one of the things that is known theoretically about the shape of the neurons, it's not as helpful as you might think, but it's just that if you're not linear, and it's almost as simple as that, but pretty much any other shape that you might want to use has this universal approximation property. So we know that these neural networks are capable of approximating any sufficiently smooth function with an arbitrary degree of accuracy if we've got big enough neural network and feed it with enough data. Okay, and that's been highly motivating for many people, and including me. So you kind of know that, like in principle, at least this tool can solve my problem. Even if today it's not solving my problem, then that leads you to the question of how should I change it to make it do better, rather than, well, maybe I have to just throw this away and look for some completely different technology to help me. Okay. Now, if you look at the proofs for these things, they do make some general assumptions about about shape of the activation function, but they're really very general. I mean, almost any shape seems to be fine, except not linear. It can't be linear. It can't be the 0 function. Like the ridiculous things are ruled out, but like almost everything else seems to be fine. And what the proof will do, if you look down into the math, because I have looked into the math, is they will generally just construct a neural net of 1 hidden layer, which is the picture actually from the last slide. And then they will show that for any function you might be interested in approximating, as the width, which is the number of hidden units in that 1 layer that you have, approaches infinity, that the error goes to 0. Yeah, which is quite a remarkable fact. Now, more layers should only be better, right? If you can do it with 1 layer, you
it shouldn't hurt you to use more, assuming you're reasonably intelligent about things. However, not that's kind of understating the case because again, not due to any deep theory, but from a lot of experimentation, we've come to understand that actually, if you've got a budget for how many neurons you can afford, how many parameters you can put into your network, and you have a choice of either building a monster wide network like this one, but really shallow, or a deep network, you're probably better off with the deep network. Again, no guarantees associated with this. It's just that people have seen it time and time again in different domains. And when you hear about deep learning or deep neural networks, that's the deep that they're talking about. To use, because that was one of the things that kicked off the latest renaissance in neural networks, was the idea of let's try making them deeper. Oh, it seems to work better. Okay. All right.
Yeah, back to what you can use these things for. So we already were kind of steering around this, but just to cover the slide. So you might, so learning to represent a functional representation is a general thing of interest, right? If you understand what linear regression, if you said you're learning linear regression, right? And Samsung said, well, what's that for? What, is it for biology? Is it for economics? Is it for some military problem, XYZ? It's like, yes, you're like, it's a tool, it's like, what's a hammer for? Anything you need to you need to hit something, you maybe want to reach for a hammer, it's just a tool, but it's a powerful tool. If you can predict economic outputs given inputs, that might help you plan your investments better. It might help you run your economy better. There's just no ends to that. So that's not on the slide because that's just always there. But so speaking of AI uses a function representation, and we're not economists or biologists today. So we could think of something like, remember the evaluation functions? Well, if you're doing game tree search, and you realize that there is no way you're actually getting down at the beginning of a chess game, you're never going to see a terminal state. Those just aren't going to be visible. You're going to need an evaluation function to guess the value of a state. Okay, well, that's a function that will take the game state, the chessboard, what have you, and produce a number. How good is that state? Now, as we discussed before, the original evaluation functions came from people who just wrote down a formula. That's fine too, but could we not use a neural net to do the same job and do it in a data-driven way versus some individual's guess? Yes, we could. Okay, maybe we'll do that by the end of the quarter. That's what I'm thinking of for the last lab. That connects very nicely what we'll do for summer. Okay, we also could create discrete probability distributions, okay, where we'll want multiple output values for those. So typically, if we have a classification problem with n classes, right, it's not just cats and dogs, but it's cats and dogs and birds and snakes. Okay, if we have 4 classes, we typically just have 4 outputs. One is redundant, as you'll realize. Okay, but we typically have 4 outputs. Each one is supposed to give us the probability that the example is in that class. Okay, another thing that we like to build, another kind of probability distribution, is a policy. So here the outputs represent actions that could be taken in a particular situation. And the policy should tell us which ones are the ones we should take with higher frequency in this situation. So what are the good actions to take in this situation and the relative probability with which we should take those, including in the most complicated settings, including in adversarial situations, as factors in the fact that, well, you don't want to be predictable. It's not just what's good, it's also what's good when we don't want to be predictable. All right. So we have a lot of uses for function representation and function learning, even just in the little world of AI. Okay. And then the next lab will be a function learning lab, where I'll give you some data and say, go ahead, model it as best you can, and then I'll look and see, compare how you guys do to one another and to myself. See what we can learn. Okay, so
let's see, I'll just kind of follow the slide here. So it's saying assume we have a functional relationship between two variables x and y. More typically x will be high dimensional and y may be high dimensional too, but Blackboard stuff, right? So it's good to have an x which is one dimensional and a y which is one dimensional for learning, just to get learning done. Okay. So let's assume that we don't know the correct form of the function. Okay, we don't know. So if there was theory telling us that it was probably a line, we'd be fools to do anything other than linear regression. If we knew a particular shape, like it was going to be a parabola, because we know it's physics and it has to do with acceleration, and we know the data is going to be parabolic. Again, there's probably other special techniques we could use, but very often, if it's what images are cats versus what are dogs, we don't have a theory about that. I don't anyway. So I'm open-minded, It's complicated. I understand it's complicated, but other than that, I don't really know what the function needs to be. Okay, and we're going to assume that we're going to do this based on data, not on theory, but based on data. We have examples of XY pairs that come from that function. Okay, and that's what's kind of diagrammed out here. Now you'll notice I'm kind of showing you what one possible function might be, right? And the data isn't right on that line. Well, that's because typically data from the real world has noise in it. Okay, there's some amount of measurement error. Sometimes other kinds of error as well. So the problem of function learning is given the circles, but not the red line, you tell me the red line, and that's what you'll be doing in the lab. And you give me your take on what the function should be. And it's not obvious, right? Like this two-humped camel kind of shape. I mean, I don't know. If you just look at the circles, try to tune out the red shape. Is it really a two-hump thing? I mean, maybe it is, but I mean, it might just be a line, and it these are just artifacts that it does kind of look like these are kind of high, these are kind of low, high, kind of low. Okay, so we're hoping for a technique that'll do a good job of making a guess, which is what it will be at the end of the day, but it'll make a good guess as far as what that function could be. Right? And then we want that because, of course, we want to use this for prediction. We want to be able to say, if you say, okay, I now need to know what the function should be at 7.5. I might have no data point exactly at that point. And even if I did, that data point would have noise on it. So you would go up and index against your model, the red line, and say, okay, that would be my value, 3.25. Okay, fair enough? All right. So we decided we're going to try to learn a function. Okay, what do we need to do? So the first thing you need to do is pick a form for the function. Now, we've been talking about neural nets, so that's kind of a no-brainer choice. It's not the only possible choice. Whatever your choice is, it's bound to have some parameters in it. That's what you're going to be fitting, right? So if you choose the family of parabolas, that will be different from the family of neural nets, but it still is going to have some parameters in it that you're going to have to fit. Right? What's the parabola centered on? Does it have a linear term in it or not? Is it tilted to one side or the other? Is it up or down and all that, right? Okay. So we write this as f. We're trying to make a function of x, but we're putting in this extra theta there, which holds all of our parameters in our trainable function. Okay. And the goal is going to be to set all those parameters in theta. Theta could be one number or it could be a trillion numbers. We set all of those to make f of x close to y on our training data, and then hopefully in the future as well. All right. Now, for many applications, there are other things to do. Back in the day, when neural networks got started, there are other techniques that were used with in settings where you were going to do complicated function fitting, function learning, function approximation. So you can use things like polynomials and sinusoids. And the beauty of those is that if you want to use a polynomial or a sinusoid to fit the data, if you know that's going to be good enough, you can do linear regression rather than neural network regression, and that is often a win. Though with complicated functions, I'm not sure it's always a win. And that's just my ignorance. Ask your stats professor what he thinks about that. He or she thinks about that. All right, and you know where to get the special techniques. That's over in stats lab. Okay. All right, so we're going to use neural nets. This is not linear, but non-linear regression, and the techniques are going to be different. We're going to use hill climbing search to set parameters. Okay. Now, for function learning, for this particular application, it's not classification, it's not producing probabilities on the output, it's producing any floating point number, right? Because that function could be doing anything, positive or negative, huge or small. So the output layer typically then contains a linear unit or linear units if the function is multi-dimensional. Okay. And then the next thing you're going to do is just kind of say, okay, if you're charging me, okay, here's your data, set a function to this, like what's your error measure going to be? Okay, you have to actually give me an error measure. Typically the squared error is typical. Does that make sense to you guys? Is that, you know what I'm talking about?
If we did statistics.
Did it in statistics, good.
I have my own picture just to make sure we're communicating, but yeah, I assume you know it from statistics. Okay, so here it is in math on the page, right? So if these are my samples from my function, my otherwise known as exemplars in neural network lingo, then my error measure for my function f, neural network or not, you know, this is independent, okay? It's going to be a neural network for us, but it could be anything. Will just be what I get by summing up the difference and squaring it, and usually averaging. So you get the average squared error. Okay, now squared error is not the only choice. Do you realize that? Did they give you other choices in statistics? What do they talk about other than that's not squared error? Did they talk about anything?
I mean, they introduce error by not doing square to some regular error. They square.
Oh, just a signed, right, like a signed error kind of a thing. Okay, okay. All right, well, there are other options other than squared error. So squared error is, you know, it's a particular choice, and it might be perfect for you. You know, often when we know that the noise, so there is some theory there, whereas like if you know that the noise that's on the data is Gaussian, is a normal distribution. Now, I don't know when you know that, but a lot of things look like normal distributions. So statisticians love to just assume things are Gaussian. If it is Gaussian, then there's a theoretical connection to squared error that makes it a particularly good choice. I don't recall all the logic, but that's what I recall. But in general, if you don't know that, and for most situations, you won't realistically know that, then you have to think about it in a coarser way. So one way to think about what the squared error does is it's an error measure that really hates to have even one or two places in your function where it's far off from your training data, right? So what we're talking about is this is my function that I fit, right? If we're just a little bit high and low and so forth, all as well. Okay, but what this thing hates, if you're almost dead on with all these points, but there's one point over here where you're way off, it really hates that. We'll give you a bad score. Why? Because the square is going to make this error dominate the rest of the sum. Okay, so you need to think for you like, is that reasonable? On the other hand, you could be thinking, you know, I know where this data came from. I'm almost positive there's some real junk data in there. Okay, then this would be a really bad choice for you, because it's going to care about the junk data is what's going to drive what it's going to say is a good fit or not. Okay, so well, be thoughtful about it. And because, you know, the square law is kind of just described here. It's kind of, you know, like if you're off by 2 at one point, that's the same as being off by 1 in 4 different locations, right? Just to emphasize the point, right? Do badly in one location, it counts for a lot. Okay, so keep it in mind. And there's other alternatives. And like, so just to, the other obvious one, to me anyway, is to just use absolute value instead of the square. Right, so that will be less sensitive. It's not like it's going to ignore data that's way far away from the curve, right? It's never, there's no approach in which it's a good thing to have data that's way off the curve that you're trying to fit with, but it will be more tolerant of a few bad points that are way off the fit than a squared error choice. So think about it. Okay, yeah, again, just to give you the, here we have our points, here we have our fit, right? And if we evaluate the actual, what the fit says the value should be at each one of those points, and then measure the displacement between the two, and then square it and sum it, that's, well, all the squared error is. Okay, so we can use hill climbing search, but now this is the point at which the language flips, because now when we're doing function fitting, we almost always think about the error of the fit as being something we want to reduce rather than thinking about improving a quality of fit. That's just what the field does. Now notice that, minimizing the error of the fit is the same as maximizing the negative error of the negative of the error of the fit, right? So if it really bugs you and you only want to be consistent with what was earlier in the slides, you can at least do that inside your head. But from now on, usually I'll be talking about not quality, but a cost, but an error, and we'll be trying to minimize that error. Okay. Let's see, neat. Okay. I don't know whether I want to speak to this slide in detail or not, but at least if you ignore this piece here, you ought to recognize this, right? So say theta sub k is one of the parameters that we're trying to tune, right? And what is the continuous version of hill climbing search, i.e., gradient ascent, now gradient descent tell you to do? It says to take the derivative. This used to be a quality function. Now it's a negative error. Take its derivative with respect to that parameter, multiply it by a constant, and add that to the value. That's what this delta means. This is how much we're going to change that parameter every time we step through the algorithm. Okay. And if we look at before, if what we have is a sum of squares, right? If so, this is the negative is the negative, eta is eta. Okay, and the rest is that we had this squared before. What's happened is that the 2 has come down, taking the derivative with respect to the first function here, that we're taking everything inside the brackets as just one thing with the place at which we're evaluating that function. So it's 2 times what used to be a squared function is now just the object itself raised to the 1 power. Okay, and then the chain rule says, okay, and then you multiply by the derivative of what's inside there with respect to the variable you're taking the derivative of. Okay, and y sub I doesn't depend on the parameter, but f sure does. So this is what we end up with there. And divided by n, that's just part of the sum that we had before. Okay, so hopefully the parts make some kind of sense there. I'll show you some smaller examples in a minute now, where we do a little bit of chain rule stuff. Hopefully, you'll see they all kind of come down to, if not the exact same, they're all very similar. Now the note at the bottom here is, note that to take one gradient step, you're going to need to do this sum, right? That's what it tells us we need to do. Okay, so we have to iterate through all n samples. Okay, is that a lot? Well, sort of big data, right? So in some cases, at least, n is quite a lot. Okay, and we know that we want eta to be small, and we just want to take a small step in the direction of
the gradient in the derivative direction here, because we know the derivative is only reliable very close to the current value of our parameters. So we're going to do a lot of computation to do one tiny adjustment, and one asks, is it worth it? Well, maybe not if we had an alternative. So let me show you an alternative. So one of the main algorithms that's still used, and you'll see when we use a neural network package, this is a thing. You can just like press a button to turn it on. It's been used forever, like all over my entire research career. I mean, my thesis was about this algorithm, my dissertation, a stochastic gradient descent. We said before is gradient descent. This is stochastic. Stochastic, as you know, means there's some randomness involved. Okay, so let's talk through this. So what we're going to do is, instead of summing over all the samples, which is what the, hill climbing tells us we need to do, what we're going to do instead is not get the true gradient, but get an estimate of the gradient at the current point. And how are we going to get that estimate? Well, we're going to use just a single sample to get our estimate. So this is what was on the last slide. This is what legit gradient descent tells us to do. And instead of that, we're going to take one sample. Instead of all these x sub I, y, we'll take, this is one of them, just x, y, pick one. The sum goes away, and it's the same expression. Okay, oh, I left the divided by n in. Well, n is 1 here, so so that's nothing. Yeah, I can make it a little simpler looking. Okay, and that's what we're going to use to adjust each one of our parameters for one step of the algorithm. Yeah? Make sense? Maybe? Ask a question, Chris. You look really unhappy.
I just haven't sleeping.
I can't help with that.
Yeah.
If you need some more math.
So
Yeah.
obviously using this one instead of the last one, you're losing something in order to gain computational efficiency.
Yes.
So what is it that you're losing?
Yes. Okay. What are we losing? Well, we went from the actual best direction in which to move to reduce. We're going downhill now. Now we're trying to go downhill the steepest way. Now, instead of the best direction, we have an estimate of the best direction. What is easy to show, and in fact, I'm not going to show it, but let's just think about it. This single sample estimate is an unbiased estimator of the true gradient. Is that obvious? If the truth is just an average over some samples, and I just take one of those samples and use that for my estimate, that's unbiased, right? If you take the average over all the possibilities, you get back to here. So on average, it's the right thing. It's just that in detail, it might be the exact wrong thing, at least some fraction of the time. Okay? So we've gone from something where, it's going to just do step, like this, to now something that's going to do who knows exactly what. But on average, the steps will be correct. Okay, so we might still get to a good answer. Okay.
Are you random? How are you selecting the sample?
Various ways. You can just do a random draw with replacement. You can do shuffling of the set. Yeah. And furthermore,
is the manner that you get in danger of it not being an unbiased sample if you're not careful with how you sample it?
I suppose. I mean, if you decided to, I'll just keep using the first one. You're dead. Okay, now there are intermediates in between this. Like you might go, if you go to stochastic gradient descent and you're like, okay, I can't put up with this because it's not like this. It's actually, more like this. And you're like, I can't even tell it's doing better. It looks like a mess. Okay. Then there is an obvious middle ground, which is to take multiple samples to form your estimate here. you know, N could be anything these days. It could be a billion, it could be, it could be some huge number, but now you have control over that. You can say, you start off just trying, let's just do one at a time, and you're like, no, all right, let's do 10 at a time, because that noise is just, I think it's too much. Okay? And you play with it empirically, and that has its own name. That's called mini batch learning. You're taking just a batch of examples instead of just one and making your steps. Okay. And yeah, this is just sorry, it's written out in words rather than an equation here, but this just says that you could write this, you can write these steps, this step as being this plus noise. That's just a mathematical reformulation of what we said. Yeah, and that noise is a zero mean random variable. See, getting added on here. Okay, any other questions about this?
All right. All right, so that's good. So we covered a lot of good theory. What we'll do tomorrow is we will I'll do some other examples with the math, just a couple easy ones to hopefully let it gel you. I'm not going to expect a lot of math back from you, but it is important to understand, the solidity of what the ideas are there, and it should be well within, if you've ever sat in any calculus whatsoever, it should be well within your ability uh, to use that to motivate the use of these tools in practice, and that we will hold you responsible for. Okay, and we'll see how far we can get tomorrow, and hopefully if we get far enough, then we'll do the lab Monday. If not, it'll be Tuesday. Okay, all right, see you guys tomorrow.
You guys need some.